Okay, so the lathes, most powerful machine in the shop, probably the more dangerous of the machines. There's nothing going to stop this machine if you get caught in it. So it's really important to have, I wear a lab coat, roll my sleeves up, take my watch off, no jewelry, no long hair, nothing loose on you. Because if it gets caught here, it's about 7 horsepower, it's gear reduction, and nothing is going to stop that. So with that kind of power. So you want to be really careful on the lathes. We have 4 different types of lathes. They all do the same thing, but have different settings and setups on them. Most of them have a safety, which I use all the time. Turning it to the right powers the machine up, pressing it in stops it. All that's going to do is stop the machine. It's not going to stop the chuck from rotating when it's running. I'll demonstrate that. And you can see it coasts to a stop. I push the lever down. Now it's off. Turn it back on. I'm going to turn the chuck on again, spindle on. Up is forward. Now, 5 of the lathes have safety brakes on them, and that's down on the floor. If there was an emergency, that will stop the motor and the chuck. It's your best bet for stopping it quickly. Then you have to reset it, and it doesn't depress this when you do that. It just stops it. So we've got 4 of them with a safety brake on. Okay, so when you're setting up to do some turning or lathe work, I always turn the safety off. That way, if I turn the spindle on, it doesn't move. We've got safety chucks, so keys, so the spring pops it out. Now that pops it, it's hard to leave it in there. It's possible, but you never want to leave the key in the chuck. I'm just going to put a piece in and demonstrate that. You don't want to hang the part out more than 3 times its diameter is safe. 10 times is way too much. So if it's a 1-inch piece, you can't hang it out 10 inches. 3 inches would be appropriate, and probably you would get the least deflection. And when I tighten this, I really tighten it. Some chucks have more than one wrench spot, and you can tighten it several places, but I brace myself and tighten it really good. The tool holders, of course, these can rotate on the compound, and the cross slide is just one direction in X. I want to make sure that everything's tight. So if this were just finger tight and you came in to cut, it's going to spin it and move it. So I'm going to try and do 2 things. Line this up on center and then make a cut. So I've got the tool angled the way I want. Tight. And I do check the compound. Make sure that's tight so it doesn't rotate. All right, so you've got a choice of live centers, drill chucks. Keep the tools with each machine respectively. They're kind of unique to each bore and spindle. The tailstock, I can just use this. This is a tapered fit, a Morse taper, M-O-R-S-E, and it's just a friction fit. It's under a 2-degree angle. That makes it lock. Unlike the mills, which have a steeper angle, the R8 taper does not lock. It requires the drawbar. To remove that, I just turn the hand wheel back, and there's a bolt in the center, and it pushes it out. So bring it forward a little bit, clean it off real good. I usually check the bore, wipe it out with a rag, and then my clean hands, and just snap it in. I'm only putting it in right now to show you that it's one way to set the height of the tool. As long as you can get to it and see it, you can see that the tool is about level, might be a little high. Loosen that. You can drop this down a little bit. See, that can come in and out. Tighten that up real good so nothing's going to spin. A second way to check center line is if you have a pocket scale, a steel scale, you can bring this in, touch it lightly, and look at it for vertical. And if it's centered, it's going to be vertical. If it were high, it's going to tip it forward. This is a quick way to check center. And then if it were low, it would tip back this way. So that's just another trick to check center. Make sure it's tight. Tailstock is locked with this lever, and it can't move here. And then if we're turning between centers, which you've done in your labs, you can lock that when you have pressure on the bearing there, and it won't move. Okay. And then when you're done and clean up, I would like the lathes to be wiped down and oiled, and you can bring the carriage all the way back. Take this tool out, put it in the rack. Slide it to the back. It is possible to slide it off the end of the lathe too, so don't just push it back. Alright, so your speeds and feeds, your RPMs, I put some charts in the shop all around speeds and feeds. These have to do with the different materials from aluminum softs to titaniums, steel hardened. You're going to look at your surface feet per minute that's recommended for carbide tooling, which is mostly what we have. You're going to pick a diameter, say 1 inch aluminum, and you can have a feed rate on the lathe or the mill, 0.008 of an inch feed. And then you look over at the machine itself, and here's 0.008 feed. So you can look at that chart and calculate your RPM. Don't just run it as fast as it'll go or as quickly as it can go. Just look at that chart. There's some information right there and a couple of formulas, simple formulas for RPM, inches per minute for your feed rate, or how fast you should feed per revolution. Just basically 3 simple formulas, and you can narrow down your speeds and feeds. So when I'm going to feed automatically, I just look at these numbers, LCS4W. There's your 4, C, maybe. It's a little difficult. You can see I'm spinning the chuck and I'm watching the lead screw turn here. So I know it's engaged. S. Okay, 4, W. All right. Safety off. Spindle on. And there's your feed. Try this away from the chuck before you are close to it. I like that speed and RPM. It matches what's on the chart up here. Now, if you're coming close, I can show you a couple of examples of cuts. This is aluminum, and I'm going to give you an example of a light cut. 30,000ths of an inch depth of cut is probably a maximum. I come up and touch, that's about 1,000, and I can use the digital readout, or I can use the numbers on the dial here. 10, 20, 30. So 30 thousandths, I'm going to feed it by hand. You can see I'm getting an excellent finish, and you can get an idea of the feed rate that I'm using. Now I'm going to increase the feed. And you can see the quality is reduced. So feed rate here, I was doing that by hand, and that was probably about 8 thousandths feed per revolution. 8 thousandths feed forward in Z per revolution around. So I'm going to take another cut, 10, 20, 30 thousandths depth of cut. We're going to turn it on. I'm going to use the automatic feed now and give you an idea. 30, and here's automatic feed at 8 thousandths. It's a nice even chip coming off, but it's coming at me. You want to be really careful with your hands. All right, so finish was excellent. 8 thousandths feed, and one of the more important things about the lathe is, as tempting as it is to just pull these away and throw them away, never grab these. What's more likely to happen is it's going to wrap into the chuck and strip it through your fingers and cut your hand badly. So we usually have brushes, chip brushes out on the bench or out on the machine, and you'll just sweep those away between every cut. All right, so I'm going to show you a little heavier cut. I'll show you too heavy a cut. So that was 30 thousandths depth of cut. Now the machine is probably capable of, much heavier, especially in aluminum. This is about a 100 thousandths depth of cut. Now you can hear it, a lot of vibration. I can still reduce the feed rate and get a good chip, and I can push harder. So you can see that the machine is capable of a much heavier cut and much higher feed rate. But your quality is going to be low, and you can hear it taxing the motor. And the quality and the size is not repeatable that way. So you're going to probably take about 30 thousandths depth of cut max, which has to do with the nose radius of the tool here. And that would be important to not cut too deep or too fast. In steel, we would reduce everything down and go by these numbers on the chart. Carbon steel surface feet per minute, 150. I would start at the low range and then work your way up if you're trying to get better finish. Okay, then we'll move over to the mill.